All right, it's 6:10, so we're gonna get started. So welcome everyone to the Arduino Workshop. This is being held by the University of Toronto's IEEE Club. There are 5 mentors with us today, and we're just gonna go around and introduce ourselves with our program and year. So I'm Selena, and I'm ECE 2T3.
I'm Kushagra. I'm also in ECE 223.
Greetings, my name is Fahim. I'm in ECE and I'm 2T2.
Hey guys, I'm Steven. I'm also EC2T3.
All right, so before we start, we're gonna go over the agenda real quick. If you can move on, yep, okay. So we're gonna briefly go over what the Arduino is, and then a bit of introduction to some hardware components that you'll see working with the Arduino. And then if anyone still has any problems signing up with tinkerCAD, we'll have like a little bit of a break there just to figure out those issues if we need to. And then we have 4 interactive activities that we're going to be working together through on tinkerCAD. So this will be working with an LED, motors, and some sensors. And then finally, we'll wrap it up with some videos on some projects that other people have made with these components and the Arduino. So yeah, if there's any questions that you guys have, please send it in the chat, and then our mentors will respond to you there, or if needed, we'll bring you to a breakout room. Okay, so we can start with the next slide. Okay, so the Arduino is basically an easy-to-use hardware and software component that you can see in the bottom right. It's a picture of the board. So this is basically a circuit board with LEDs, a microcontroller, some pins, and other hardware components that basically is easy to use and can help you control other pieces of hardware such as sensors, buttons, motors, etc. And we can work with the Arduino through a programming IDE, and that's the Arduino IDE. And this is basically where we can code and then send these instructions to the board. So if we move on to other pieces of hardware that you'll see working with the Arduino, I think Kushagra, you got that part.
Yep. Thank you so much, Selena. So the Arduino is an open source hardware platform. What this means is that you can create one at home or even modify it using off-the-shelf components and the designs given on their website. All the schematics and designs are available for free. This is what we'll be using as the brain for our projects today. The Arduino is a very tiny version of the computers that you and I use today. Generally speaking, it can run only one program at a time, as opposed to multiple simultaneous programs that our computers run. The breadboard allows us to connect different components using wires. It is essentially a whiteboard with tons of holes which are internally connected. LEDs are small lights which run on DC voltage, and resistors are devices which limit the flow of current in a circuit. Now, whenever you open up a commercial electronic device, you'll most probably find a green colored board with electronic components glued or soldered to it. This is called a PCB, or a printed circuit board. These are permanent circuits and cannot be changed. We'll be using breadboards for the circuits we design today, which allow us to easily change our circuit and remove it after we're done playing. This means that breadboards are reusable, whereas PCBs are not. Very soon, we'll be looking at how breadboards are internally connected. The code that we write for the Arduino board is in a language called Arduino. This language is a derivative of C, which has been simplified so that beginners can easily start working. The Arduino IDE has all the tools needed to write, compile, and upload your code to the board while it's running. The cable used is a USB type A to B. This is the same cable used in most printers. Now let's take a look at the board itself, specifically the pins. The analog pins in the red circle are used to measure variable things in nature, such as temperature, humidity, brightness, etc. These are things that have different states. The Arduino perceives this data as some voltage between 0 and 5 volts DC. The digital pins in the green circles are used to measure things which have only two states, such as a digital signal, like a button. either on or off. These pins can also generate a two-state signal, either at 0 or 5 volts, which is the logic of the Arduino board. They can also simulate voltages between 0 and 5 volts using a technique called pulse width modulation, or PWM, which we'll explore later. But there is no true way to generate actual voltages between 0 and 5 volts on the Arduino board. It will only be a simulation. The reset button in yellow allows you to start your Arduino program from the beginning. The VIN pin in the pink circle directly connects you to the Arduino's power source. This is a value between 6 to 20 volts. The 5-volt pin, also in the pink circle, provides regulated 5 volts DC, and the 3V3 pin provides regulated 3.3 volts DC. The GND or ground pin will act as the ground for all of the circuits we build on the Arduino, and we can use any ground pin that we have.
All right, so right now we're gonna have a bit of a break just to talk about tinkerCAD before we start with the activities. So if anyone hasn't signed up for tinkerCAD yet, could you please message us in the chat, and we can sort of help you out and then get you set up before we start the activities. So right now is that time. If there's no one that needs help, you can always message us later on when we're starting the activities, and we can bring you to a breakout room to try and figure it out. But yeah, if anyone has any problems with signing up or hasn't signed up yet, please message the chat. We'll give like another minute or two if there's no one. Okay, right now, so I think we have a bit of time right now. If we want, we can go through how tinkerCAD sort of works, but I think Kushagra, or sorry, Fahim is next, or Kushagra.
I'm next, Lena, and
Yeah.
I'll be covering the tinkerCAD UI a bit.
Okay, so if there's no one who needs any help with setting up, we can move on to our first activity.
Okay, sounds great. So, in this project, we will get a simple LED to blink by repeatedly turning a digital pin on and off. The circuit, as you see, is relatively simple, with the anode, which is the positive terminal of the LED, connected to digital pin 13, and the cathode, which is the negative pin terminal, connected to the ground through a resistor. The resistor is needed to ensure that we limit the amount of current passing through, since LEDs have very little resistance on their own. Not using a resistor will mean too much current will pass through and you could burn your board or the LED. So now let's head over to tinkerCAD and explore the UI a bit. So I suggest you all put this presentation in split screen, or if you have dual monitors, put the Zoom call on one monitor and tinkerCAD on the other. So I'm going to wait for a second while everyone does that. And once you're done, head over to the dashboard and you should be able to see the same screen that I have on. Great. So let's begin. So what we want to do is go to the circuits tab in the left pane, and we want to create a new circuit. Great. So we have our canvas open. It's empty for now. And you'll notice that we have a pane towards the right containing tons of elements that we can add. So let's start by adding a breadboard. So you can search for a breadboard here, and I'm going to add the small breadboard because that's the easiest to work with. So you can just click and drag it onto your canvas. And it should look like this. Don't worry about giving it a name since we're only using one. So the breadboard, as I mentioned before, is used for prototyping. And on this breadboard, we can easily change the circuits that we create. But before that, we first need to understand how a breadboard is internally connected. So all the holes on the topmost and bottommost rows are connected horizontally. What this means is that all of the pins highlighted in green are connected to each other. For this row, for the second row, and for the last two rows. These are generally used as power lanes to provide DC or AC voltage and a ground. The holes toward the middle are generally used for prototyping. They are connected in short vertical columns. So the first column has 5 holes connected to each other. Similarly, the second, third, fourth, fifth, sixth, seventh, and so on. Keep in mind that the top column and the bottom column are not connected. Only 5 holes on a column are connected to each other. Now let's try drawing a wire. Just click any hole and you will start to create a wire. As you can see, if you connect it to another hole, you will create a connection. You can also bend a wire by clicking on an empty space while drawing it. So this allows you to create much more cleaner circuits. To delete a wire, just select it and hit delete on your keyboard. You can also change the color of wires by selecting it and choosing the color that you want. Of course, this doesn't really matter and the application of your wire does not change. Now, let's take a look at another component, the LED. So I have it right here. I'm going to drag it and drop it onto my breadboard. Or let's take a look at it first. So the first thing that you notice is that one pin of the LED is bent. In real life, this pin will be longer than the other pin. This long pin is the positive terminal of the LED, and it is called the anode. The shorter pin or the straight pin in this simulation is called the cathode, and that is the negative terminal. You can also change the color of an LED in this menu and keep it to any color that you want. For now, I'm going to go with red. Great, so let's start building our circuit. In the right pane, I'm going to search for the Arduino, and you can find it here under Arduino Uno R3. So I'm going to drag it and drop it onto my canvas beside the breadboard. Now, let's take a look at the circuit again. So we're supposed to connect the LED, the anode of the LED to digital pin 13 through a resistor and the cathode to a pin to a ground pin. So let's build that now. So let's connect our LED anywhere on the breadboard. So I'm just going to choose this place randomly. The next thing that we have to search for is a resistor, and we have it here. Now keep in mind that resistors are not polarized. What this means is that resistors do not have any positive or negative terminal. You can connect them however you want. Now I'm going to draw a wire from digital pin 13. You can use the wire sort of snap onto this on these blue guidelines, and that sort of makes for a cleaner circuit. I'm going to draw a wire and I'm going to connect it to the resistor. Now, if you remember what we just discussed, technically the resistor and the wire are connected because these 5 holes in this column are internally connected through the breadboard. The resistor is connecting with the LED through its positive terminal, the anode, as the resistor is crossing over the gap. Now I'm going to take another wire from the negative terminal of the LED and I'm going to connect it to one of the Arduino's ground pins. So I'm going with the right ground pin. You can also use the left one. And our circuit is complete. Now let's move on to the coding part. So you want to click the button titled Code beside Start Simulation. It will open up another pane. Beneath the code button, there is a menu which says Blocks. We're going to click it and select Text. We want to continue. And here we have the basic code for to blink an LED. Now, let's look at the Arduino code framework a bit. Void setup is actually a function with the name of setup. On the Arduino, the setup function runs once. In this function, we are telling the Arduino to we're telling the Arduino that we are going to use digital pin 13 as an output. Now, you might remember when we were introducing the Arduino board, I mentioned that the digital pins can be used to generate a signal or sense a signal. In this case, we are generating a signal to use it as an output. So I'd suggest writing the code along with me. Please be mindful of the capitalization. It is case sensitive. So the pin mode has to have a lowercase p, and the M of the mode has to be capital, and the output has to be all in capital. Every statement in Arduino and C++ ends with a semicolon. So be sure to remember this. So I'm going to pause for a few seconds while everyone writes the setup part of the code. Okay, let's move on to the second function called loop. So while setup runs only once, loop is the function that keeps on repeating, hence the name loop. The next command that we see is called digital write. This command is used to generate a signal on a digital pin. So please be mindful, digital is all in lowercase, write has the W capital. We want to specify the pin number, that is 13, and high. High means to generate 5 volts on that digital pin. So what this command will do is it will turn our LED on. Don't forget the semicolon. If you forget it, it's going to cause you tons of problems. The next command is the delay command. Now, because the Arduino runs at a speed of 20 megahertz, if we write commands one after the other without telling it to pause, we won't be able to see what is happening. So we want to tell the Arduino to pause to let us observe what is happening. So in this case, once I have turned my LED on, I am going to tell the Arduino to delay or pause for 1000 milliseconds, which is 1 second. Again, don't forget the semicolon. Next, we issue the digital write command again, this time turning the LED off. And the way to cancel a signal on a digital pin is by using the low parameter, which is the exact opposite of high. Once we tell the Arduino to turn the LED off, we will again make it pause for 1000 milliseconds or 1 second. Now, once this delay is executed, it will again go back to this first command because this function loop keeps on repeating. And as probably everyone has guessed by now, this is how we're going to simulate our LED. So once everyone is done writing the code, you can go ahead and click Start Simulation. And you'll see that the LED blinks at an interval of 1 second. Okay, so this is a simulation. Now let's take a look at what this looks like in real life. So you can see that the Arduino being used here is slightly different. That is an Arduino Nano. In our simulation, we were using an Arduino Uno, but it's essentially the same. All the pins are the same. It works the same. It's just a different size. So you can see a resistor here. There's my LED, and I'm using these wires to connect it to the relevant pins. Now, let's take a look at a challenge. can we have a series of 3 LEDs blinking one after the other, like so? This is possible using everything that we've learned right now, the circuit and the code. So I'm going to pause here for a few minutes so that everyone can attempt this on their tinkerCAD simulations. Please feel free to post any questions that you have in the chat, or if you need help from a mentor. And we'll resume soon. Please feel free to unmute and ask any questions if you have, or post them in the chat. Great. So I hope everyone was able to give a try at this. So are we ready to see the solution? Okay. So let's go back to tinkerCAD and I'll open the solution. Okay, so your circuit should look something like this. You are free to use any digital pins you want. I stuck with 13 and I added 7 and 4. I also made use of this rail on the breadboard, but you didn't have to. You could directly connect all of these LEDs grounds to separate ground pins on the Arduino. But using this rail makes it really helpful when you have multiple components. So as you can see, all of these wires are going through a resistor into the positive terminals of the respective LEDs and to the ground through a common line. Now let's examine the code. So as I've used pin 13, 17, and 4, I have to declare these pins as an output before I can use them. So in my setup function, I have declared 13, pin 13, 17, and 4 as outputs using the pin mode commands. Okay, so let's examine the loop function now. I first turn digital pin 13 high. So that is my green LED. Then I wait for 1000 milliseconds or 1 second. Then I turn it low. I turn the LED off. I wait for another 1 second. Then I turn pin 7 high. Pin 7 is my yellow LED. I wait another second. I turn it off. I wait another second. And then I turn pin 4, digital pin 4 high. That is my red LED. I wait another second here. I turn the red LED off and I wait another second. So let's start the simulation and you'll be able to see these three LEDs blinking one after the other. So I see a question, is there rationale behind the indentation in the code? So not at all. So I can remove or I can add as much indentation as I want. C and C++ and Arduino do not really care about your indentation. What they do care about are your semicolons. So I'll add random indents and you'll see that the code will still work. Great. So I hope this was a fun exercise and I'm now handing the presentation to Fahim, who will take you through the sensors part of the presentation. Thank you.
Oh, hello. Thank you, Kushagra, for passing that on to me. Yeah, so hey guys, my name is Fahim. As I've said before, I'm in EC222. So what we're going to learn more about now are going to be ultrasonic and infrared sensors and how we're going to make them. But before that, we should describe exactly what sensors are and why they're useful to us. So a sensor gives you very precise measurements, and the reason why they're very useful for us is because when you make a control system, you want to have some sort of loop where you can continually check the feedback and the feed forward of your system. And the reason why it's important is because there are a lot of safety precautions in daily electronics applications. For example, you want it so that when a car approaches an intersection, there should be a sensor there to detect whether or not there are a bunch of cars waiting for a left turn. And if those cars are going for a left turn, then you want the left turn signal to be up for them once their traffic lights hit green for them. So other than traffic moderation, there's plenty of scenarios where you'd want to use a proximity sensor. Many situations where you want to use an infrared sensor is for heat detection. So that can be for detecting when someone's entering a room and checking the temperature to see how much, what exactly is the temperature inside of a room. It's also very useful when you're changing the channels or the volume on a remote for your TV. So as you see here, we'll start with the proximity sensor, and the pins are the following: VCC, trigger, echo, and ground. We'll start with the power supply pins. So the ground has to be connected with respect to the VCC. So long as there's a difference of 5 volts, there shouldn't be a problem. But typically, for the purposes of our own reference, the ground should be 0 volts, and the VCC should be connected to the 5 volt supply. Now, the trigger and echo pins are what defines the ultrasonic sensor. The way that an ultrasonic sensor works is that it senses a pulse, and that pulse has a certain speed, typically the speed of sound, at least approximate to it. And based on the distance that it travels, aka to an object and back, we can measure the amount of time it has taken for its travel. And based on a simple calculation of distance equals speed over time divided by 2, because it traveled twice to the object and from, we can figure out the distance of an object with respect to the ultrasonic sensor. Here's a quick demo of what that looks like. So as you can see, all the values are popping up in the serial monitor. You can see me moving my hand back and forth, and as you will see right now, the values for the distance are changing. Cool, so let's go build that right now in tinkerCAD. So feel free to name your circuit whatever you'd like. And as you've seen before, we could start off and drag and drop a breadboard, but because we're engineers and we like to be efficient, we'll have something pre-built for us. Now, as you can see here, in the style that Kushagra has shown us before, we'd like to connect all of our feedback back to one of the rails, to and from the rails, as they are our power supply. So in this case, our 5 volts will be supplied on the positive rail, and the ground, in this case 0 volts, will lead to our negative rail. So the first thing we're going to need is obviously the ultrasonic sensor. I'll put that right here. We're going to connect the power lines. Now, although this is completely personal preference, I'd like to have the power lines for the negative rails to be black. Oopsie doopsie. Black and red in particular. So for the negative rail, it would be black, and then for the positive rail, it would be red. And then now we have to connect our trigger and our echo pins to one of the sockets in the Arduino board. So personally, I've chosen that to be the pins 9 and pins 10. And in terms of the circuit itself, at the moment, we're basically done. Now, of course, there's a coding portion, which we'll show you right now. Technically speaking, you can do this in blocks, but in the Arduino IDE yourself, when you do the more hands-on approach and when you build circuits in real life, you want to stick to text. So that's why we want to encourage all of you to try to program this using the Arduino IDE, typical Arduino IDE setup. So before we start typing in anything for our void setup and our void loop, we want to declare all the pins that we need. We'll declare them as constant to make sure that we can't change them in the future. So in our case, we're going to have our trigger pin set to 9. And just to make sure, I'm going to follow the path to see if that is the case. Indeed, that is the case. We are good. And then we're going to set up our echo pin. Now, echo pin is supposed to receive the input, receive the pulse that of the trigger pin coming back. So we both want to have them in a manner such that we both want to connect them to sockets that will be useful to us, right? Any socket would have worked. I'm just connecting them side by side for our own convenience. Technically speaking, I could have connected the, if you can see with my mouse cursor, the echo pin all the way to the other side, but that would look very cluttered on the actual board itself. So we choose not to do that. We're going to declare some variables. So we're going to have float duration and distance. Duration is going to be time. Distance is going to be the distance for which the pulse traveled. Right now, we don't really need the pin mode. We don't really need the pin mode command because we don't have an LED. Or sorry, we don't need a pin mode command for an LED because we don't have it. So I just deleted the pin 13 line. But we'll still need to use the function itself. And the reason we have to use the function itself is because we need to declare the 2 pins that we use, which are pins 9 and pins 10. Further, although we didn't need to do this for the previous exercise, we should do a serial.begin command. And the reason we have this command in place is because we want to monitor the output of the distances that as you've seen in the video demonstration. Typically, the baud rate or the data transfer rate for this is going to be 9600. That's what we'll set it up as. If you don't have this, you won't be able to see anything on the serial monitor, which if you're wondering where it is, it's right over here. Now we can start off, now we can finally get into the void loop. The loop is going to be what's repeated over and over and over again, as mentioned before. But as you can probably tell, because it's repeated over and over and over again, we only need to send the trigger pulse once, and it'll be once in the loop, and then it'll repeatedly continue to trigger. And so because of that, we want to initially set the trigger pin to low, then high, and then back to low. That way it'll send an output, it'll send a trigger, a pulse, for an instant before having a delay at the very end, which delays the next trigger pulse. Now you might be wondering why we want to digitally write low initially. The reason we want to write low initially is because we don't actually know the state of the pin itself when the Arduino is off. So just to make sure we don't take any chances, we want to set it up to low before. I'm just going to copy paste this because as I said before with the breadboard efficiency. Now there's another delay command called delay microseconds, and it's exactly as it sounds. In this case, I'm going to set it to something arbitrary like 2. And then here, I'm going to set it up as, again, something arbitrary, but this time a bit longer than 2, 10 to be precise. And the reason is I want it to stay in the initial low state as low as possible, because this is just to initialize that the pin itself is low. I want the pulse to be within 10 microseconds, just so that I can confirm that it takes at least 10 microseconds for the trigger pulse to be sent out. Now, after setting it back low again, at this point, we don't actually need to worry about the trigger pin anymore. The rest of it's going to be dealt with through the echo pin. So, as we've declared before, we have a duration variable, correct? So what we want is to figure out the duration of time it takes for the pulse to come back. So what we can use is a function called pulse in. The parameters are the echo pin and its state. We want to set the state to high so we can actually receive something. So that's why I set it up as it is. Then we want to make a calculation for the distance. Now the distance itself is going to be an approximation, as I've said before, because the pulse travels approximately the speed of light. So using that, we can do a quick multiplication that the distance is the duration times 0.343, because if I remember correctly, 243 meters per second is the speed at which sound travels. And we divide that by 2. As I said before, it travels to and from the object that we're sensing. Now, what we want to do is just type it into the serial monitor so that we can actually see what the results that we received are. We're going to add a delay at the end, just so that we can have time to actually read each of the results coming in. Because if you have a bunch of distances spammed at you all at once, it'll be hard for you to actually process, at which time is my hand that's coming closer to it. Is it actually reading that the distance is smaller, or is it reading that it's bigger? It'll be hard to tell. That should be all for this. So I'm going to start the simulation. Of course, as engineers, I forget how to spell. Please forgive me.
Fahim, I think there's a question in the chat if you want to.
Oh, sorry.
Yeah.
Yeah, so great question, great question. So let's see. Yeah, so 96, yeah, so the 9600 is the baud rate. Baud rate is like a data transfer rate, and the typical standard for it is 9600. Typically, as Martin has stated, the most common ones are 9600 and 115,200. Are there any more questions? Zoom into my screen a bit. Oh, okay, got you. Is that what you meant? Zoom into the circuit itself? The text portion. Got you, got you. Hopefully that's better. I think that's the most I can do. Yeah, since that should be good. Interesting. All right, so seeing as how I'm struggling with this, I'm going to spend 1 more minute seeing if there's some type of grammatical or syntactical error I made. Otherwise, I'll just copy paste it from my solutions that I have on the side. Ah, I missed an I on the 16th line. My apologies. Hopefully that'll fix it.
Also on the 20th line, you missed an I.
Ah, thank you. Yep, it is Gucci. Thank you so much for your help. Truly, grammar is my weak point. Now, if you're wondering how to read the distances, right now it's reading a fixed distance, but that's because we haven't actually changed the distances. If I were to move it further away or closer, it'll change as seen. The distances read here are in millimeters. That's why it's not exactly 67.9. So this is exactly what the demo showed. So as I go further away, say my hand were placed at that distance, that would be the distance away from the ultrasonic sensor, and if I were to bring it closer, then the distance would be smaller. Okay, perfect. Now, one thing to note is if I bring it outside of its range, it's gonna read very bad, like basically garbage numbers, right? And the reason is the trigger pin, it works on like an intersect of the waves because there's two pulses being sent out. If you do not land within those intersections, you can't get a reading. That's why outside of here, you don't get a range, you don't get a number, and inside here, you don't. So that being said, we'll go back to our presentation. Now, since you guys already know how to do that, if there are any problems, please feel free to say it in the chat before we move on, which is going to onto the challenge portion. And the challenge portion is going to be pretty straightforward. All I want you guys to do is to have an LED where it blinks at different rates based on how close an object is. So if I bring an object closer to it, closer to the ultrasonic sensor that is, the blinking effect will be quicker. The hints are as written. You're going to have to use the pin mode and the digital write functions, a conditional if-else statement or two, possibly three, and a delay statement, as you've seen before. For example, if you guys want to use, you guys can use any distances you want, but the ones I've used for my solutions are between 0 and 40 and 40 to 150. But you guys can make it larger or smaller to your liking if you'd like. So we'll wait 5 minutes for that, and 5, maybe 10 minutes for you guys to get that done. And if you guys have any questions, then feel free to do that. Feel free to ask. All right, well, hopefully you guys are done the challenge portion. I'll show you what I had for my solutions. Let's drag that right in here. So essentially, as you can tell, very lazy wiring. Only do this if you can solder. And even then, you shouldn't be doing this at all because there's a very good chance that this will disconnect. But I was in a rush at the time I made this, so this is what we'll have to work with. As you can see here, I've only added 2 lines, and in my case, it's just going to be if the distance is within this range, I'll have a smaller delay than within a larger range, for which I'll have a bigger delay. You can start the simulation, and as you can see, the further away it is, the slower it is, and the closer it is, the quicker it is. All right, so for the sake of time, I'm going to move on to the next portion, which is going to be an infrared setup. Now, our infrared sensor itself, these aren't going to be the particular infrared sensors we'll be using, but they're pretty close. They're close enough. So there's 3 pins. We have a ground pin, a power pin, which typically, just for reference sake, we want the ground pin to be connected to 0 volts, and the power pin to be connected to 5 volts. And our signal is going to be our signal pin is going to be used to detect heat. Now, this can be very useful when, for obvious reasons of temperature sensing, but it's also very useful when you're doing any infrared control. So, for example, as I've said before, remote control, changing volume or channels. So, I'll show you a circuit for that. I'll be doing this relatively quickly, but feel free to ask any questions as needed. First, we're going to need the infrared sensor. We'll connect the ground and the power pin as needed. We're gonna need the IR remote for this, because what we want to do is to have it such that every time I click a button on the IR remote, we can see the hex output that we get from it. We're going to connect our signal pin to one of the pins on the Arduino board. In my solutions, I set it to 11. So that's what I'll do here. And now we're going to have to go on with the code. Now, just for the sake of time, I'm not going to be typing out everything, because I already have a solution code with me. So what I'm going to do is copy paste stuff from my solution code into the program here and explain them line by line for you. Initially, we need to include a library that's meant for the IR remote itself, so that we can decode the values that we get from it. Next, we're going to have to declare our pins as needed. In our case, it's only going to be pin number 11 because it's the only signal pin that we need. We're going to need to describe we're going to need to classify the IR sensor itself as an object. So we call it for class IR receive. We call it IRRECV. So basically the same thing, just lowercase. And we connect it to the pin that we specified it as. In our case, pin number 11. And then in our void setup, we want to set everything as such. So, this is for the challenge portion. We can ignore that though. We want to set our serial.begin rate, our serial monitor to have a baud rate of 9600, and then also enable input by having this code. Now for our void loop, we want to have the following code. Now, in terms of this part, this should be all we need, unless I'm mistaken. Perfect. So as you can tell, whenever I click a different button, we get a different value for the hex values. And these values can help us with the challenge that comes later. Before that, though, I should probably explain what all this means. So our if statement, IR is our object name, dot decode, ampersand results, is meant to decode the values of the infrared remotes buttons that we send. So we have the ampersand here just to make sure that we get it by address rather than of the value, because if we don't put it in here, we'll make another copy of results, which we don't need because we declared it up here. We print each of the values using this field operator dot value, and we return it in hexadecimal. And then we continue on by having this, the object's name dot resume, and we have a delay of 100 milliseconds. That's about it for this portion. Now we have an IR sensor challenge, which unfortunately I'm not going to be able to give you much time for. I'm just gonna show you the final result of it. But essentially, what I wanted you to do was, you click each of the buttons. You can configure it to any, but just for the sake of my own convenience, I did it for numbers 1, 2, and 3. And for each of the numbers that I clicked, I pushed the buttons and I got a particular color of an LED. So these are the hints that you need, and you're going to need to use the results.value to print it as I've seen it, in order to access the actual values to make the comparisons. And I'll drag and drop my solution just so that you guys get an understanding of what that is. So here, when I click on number 1, I get a color red. For number 2, I get green. For number 3, I get blue. And you can see in the slideshow presentation that our demo does exactly that. I know that was a lot of information, so feel free to digest that in our break time. Feel free to ask us any questions if needed. We'll be happy to help you.
All right, so now let's just take about a 3-minute break. We're gonna cut it down a little bit just to save time. And then we'll have the servo motor and the DC motor demos coming up after this. So stick around and enjoy your virtual snacks. All right, that concludes our break. Hopefully everyone is back. So Fahim, if you would let me share the screen. Awesome. Okay. So hopefully you guys can all see my screen. All right, so our next activity is the servo motor. So the most common servo motor that you can see working with the Arduino is the Tower Pro SG90 servo motor. What a servo motor is basically a motor where you can control the degree that it turns. The SG90 has a maximum degree of 180, and other servo motors have like a 360 degree maximum, and some have a 90 degree maximum. So this one has a 180 degree maximum. So to help us work with a servo motor with the Arduino, we have to import a servo library. So a library is basically a collection of pre-written code that is configured in a way that helps us work or perform common tasks easier. So the servo library will help us work with the servo motor without getting into like the nitty-gritty of how the servo works. So to work with the servo, here I will collapse this so you can see the slide better. Work with the servo, we can first define the servo pin number, attach the servo motor, and you'll see what that means in a bit, and then we can write to the servo in like what degree you want it to turn to. So if everyone's ready, we can go to tinkerCAD. Give you a second to pull that up. Okay. So now that you're on tinkerCAD, we need the Arduino Uno, like always, and then we need the micro servo, which looks like this. So on the servo, there are 3 pins. There is ground, power, and signal. So these, like you've worked with the ultrasonic sensor and LEDs, you can click it and just move it to ground pin here. And by convention, make it black or brown. And then we can move the power to the 5 volt right here. And I will make it red. Now the signal pin, you can connect to any of the digital pins here. So 2 to 13, we can move it here. So I'll pick 7 for now, and I'll make this yellow. So this is the connection with the from the servo motor to the Arduino. Are there any questions right now? Okay, seeing none, I'll continue. All right, so now we can move to the code. So let's just delete what's already here for now. So like I said, to work with the servo motor, I will just get this in a better position. To work with the servo motor, you want to include the servo library, and do that with #include, and then in these brackets, servo.h. And then you want to declare the digital pin that you've assigned the servo, the signal pin to. So this is the signal wire, and it goes to the 7 digital pin on the Arduino. So I can do that with int servo pin, and you can name it whatever you want, -7. Next, you need to declare the servo object. So this is, the servo object comes from the servo library. So how you do that is just with capital S servo, and then you can just call it what you want, my servo. So in the setup, how you actually tell the servo where like your motor is you attach the servo pin that you've declared earlier to this servo object. So in the setup, you can do servo.attach servo pin. Next, in the loop, so this is where you can write sort of what degree you want the motor to turn to. So if we want the motor first to start at 0 degrees, so start at 0 degrees, you can do my servo, and then you can just write directly to what degree you want it to be. So this is, these commands after the dot, the attach, the write are all coming from the servo library, and you can see how it simplifies it a lot for us. So let's for now just say we're going to try and write to 90 degrees right after this. And if we do this, write 90, and then let's say we want to write to 180, and we want that to loop. If we just do this, and let's just say we run the simulation, we can see it's sort of like it's not doing what we want it to do. And this is because we need to give it some time to reach these degrees. So we can write the delay like you saw in Fahim's demo. We can just write 1 second here in between each one. So if we do that, start simulation. So if we delay it, you can see it goes between each of them pretty smoothly, but you see that when it returns back to 0, it doesn't quite move all the way back. So you can sort of experiment with this, see how long you want it to be. But just to fix that little problem, we can add 0.5 seconds right here. Oh, gotta stop the simulation and then add 0.5 seconds. So if you start it again, you'll see that it runs from 0 to 90 to 180 and back. So it loops through that. So if there are any questions on this demo right now, you can send it in the chat. But I'll show the challenge. Oh, wait, first we can show it working in real life. So again, this is using the Arduino Nano, but you can see the servo moving with the same thing there. All right, so the challenge, actually, I'll just show it here. I want you to try and make the servo sweep from 0 degrees to 180 degrees, like a smooth sweep, and then sweep back from 180 degrees to 0 degrees and have that loop, as is shown in this video. So we'll give 5 to 10 minutes for you to do that. And if you have any questions, please let us know in the chat. Oh, sorry, I'm in charge of the music, so let me add that. Apologies, I realized there is a feedback on the music. So unfortunately, there won't be music for this one unless another mentor wants to play some music.
Let me know if there's feedback, by the way.
All right, I think 5 minutes is up. If anyone has any problems, please ask in the chat. We have lots of mentors to help. So just to go over the challenge problem. So we wanted to sweep. So we have the same things at the beginning. We have the include, we have the attach, and then what we want to do is sweep. So what we can use is a for loop, and we can go iterate between 0 to 180 degrees and increment the degrees that way, and have a very short delay in between each degree so it will move smoothly, and then do the exact same thing but opposite by decreasing the degree by 1 each time with another for loop, and this will loop, let the servo motor sweep back and forth. So if we start that simulation, you can see that happening right there. Okay, and we can show this in real life. Again, just to give you an idea of that happening in real life. So if there's no questions, we can continue on to the next slide. So what we want to talk about is how this works, how we're able to control the servo motor. So this is using something called pulse width modulation, or PWM. And this is just a control technique for analog input. So that basically means when there's values in between just off and on. So for example, temperature, it varies. There's not just like an on state and off state. So for a servo motor, it's the degrees for which it turns. So how we do this with a DC current, so a DC current only has an on or off state. So how we're able to control this is by pulsing it at different lengths. So so a duty cycle is the total time that the servo motor will check if there's like a pulse. And the servo for the SG90 is 20 milliseconds. And you can see on the images here that the pulse width varies between 1 millisecond and 2 milliseconds for the servo motor. So that's between 5 to 10% for the SG90. So yeah, so this is the duty cycle, and this is like pulsing this this current, this DC current through this will let the servo motor know how much it needs to turn. So another way we can use PWM is actually controlling the speed of which a motor turns. So I think, Stephen, you're able to talk a little bit about that in the next slide.
Sure. All right, sounds good. Sorry about that, guys. Let me just switch over to the right slide. Yeah, right here. Cool. Yeah, so like Selena mentioned, we can use pulse width modulation to control the angle of a servo motor. But with a DC motor, how it works is you have an input voltage, and the speed is directly proportional to how high the voltage is. And it doesn't really make sense to control the angle there. There's not really an angle you can control, it's just the speed. So we can use PWM to also control the speed of a DC motor. Sorry, I see it in the chat. Oh, sorry, yeah, let me close these so we can see more of my screen. Cool. Yeah, so we can use PWM to control the speed of a DC motor. So just like Selena mentioned, this is a DC technique to control an analog output. With the Arduino, the analog write pins are 8-bit, so there are 255 possible states that you can control. And essentially, like I mentioned earlier, the higher the analog voltage is, the faster the motor spins. Okay, so now we've addressed how to make it spin at a different speed, but how do you make it go in reverse? I mean, what would your car be if you didn't have a reverse gear? And the way we do this is by using an H-bridge. So this controls the direction, and it's usually incorporated into a motor controller or a motor driver circuit. And the way it controls the direction is by, well, it just flips 2 switches, like in this picture down here in the bottom left. 2 sets of switches, I should say. So you have S1 through S4, which are, you can think of them like little levers. And to flip the direction of the current, all you have to do is turn S1 and S4 on, or S2 and S3 on, as you can see in the picture. And usually these H-bridges come in the form of dual inline packages. So that means they can fit perfectly in the middle channel of your breadboard with no issues. An example of this would be the L293D motor driver IC, which we'll actually be using. Cool. So if you look at this diagram in the top right, I've been displaying for the past couple slides, you can see there are a lot of wires to this one. It looks confusing, I know, but don't worry, we'll go through all the connections, and then at the end, it'll be clear. Cool. So for the H-bridge, you're going to need a 5-volt input for internal logic. This just comes straight from your Arduino. It's the same as we've done in the previous demos to control the different hardware components. The difference this time is with the H-bridge, you're going to need an external power source. This is because DC motors can draw way more than 5 volts and at higher currents. So this input can be anywhere from 4.5 volts to 36 volts for the motor. And we'll be using a 9-volt battery, as you can see on the right there. And then the L293D, the motor driver IC that we were talking about, can drive 2 separate motors. So it has 2 sets of these same 5 pins that I've listed here, 1, 2, and 2. And I'll go through these quickly. The speed control terminal connects to the analog output from your Arduino. This is that PWM output we were talking about earlier. And then there are 2 direction control terminals. These define which of the H-bridge switches are on, so it controls the current direction. And then lastly, you have the output terminals, which connect to the motor and actually drive it. All right, moving on. We will go to the demo of this. Bear with me, this will take a little time. I'm just gonna get set up here. Cool. So drag the Arduino over as normal. We can grab a breadboard. And then, oh, sorry, just want to move this down. Now we can look for the L293D, or you can look for H-bridge motor driver, but it'll be here if you just type L293. And then you can actually snap it right into place on the middle there. And we're going to need a 9-volt battery. So I'm just going to move this over a little bit. There, that's a bit too much zoom. Cool, 9-volt battery. And a DC motor. Put it right there. All right. I think that's all the components we're going to need, so we can start doing the wiring. Yeah, so I'm just going to refer to this pinout diagram here, and you can see, just to know which of the pins to use on the motor control IC. So you might have to split your screen and have that slide open along with this. But first, I'm just going to connect ground here. This is really hard on a trackpad. Please bear with me. 5 volts. Let's make this red. Make this black. Okay, so we're just giving 5 volts to these powered rails on the side here. And then we can do the same for the battery. Maybe not 1, maybe you can use a bend. Make it look better. Black and red. Cool. All right, now that we have 5 volts on this side and we have 9 volts on this side, we can start making connections to the motor controller. So the first thing we want to do, just referring to this diagram, this is actually for a 3v3 volt motor controller, but we're using the L293, which has a 5-volt input. So this pin right here, you can actually see it's labeled on tinkerCAD. It's power 1. And all you have to do is connect power 1 to your 5-volt input. Like this. We'll just connect it there. Cool. And then the other side, power 2. This connects to your other voltage source, which is as I mentioned, anywhere from 4.5 to 36 volts. In this case, it's 9. We're just gonna do that. That doesn't look great, but we'll just do this. Cool. And then you can see all the other pins are labeled too, so we'll just fill these in for this motor. So you have output 3 and 4. These are what we're going to use to actually control or provide power to the motor, sorry. So we'll just connect these up. Please let me know if there are any questions in the chat, guys. I can answer those. Yeah. And then input 3, input 4. These ones go to your Arduino. So we'll just plug them in. And these, okay, yeah, so there was a question earlier about PWM pins. And just to add on to that, the input 3 and input 4 do not need to be PWM pins, but you will see this like enable 3 and 4 pin. This one does need to be PWM. The inputs are for the direction control, whereas this one is for your speed. Just thought I'd add that in there. Boom. And then this is really messy. My apologies. We'll connect this up to 11. Please let me know if we need any of the colors to be more distinguished. I can do that. Bring it up a little bit, if it'll stay. Cool. And then lastly, we need to connect our 2 grounds. So we have two different voltage sources. So we're going to need to connect 2 sets of grounds. This one goes up here, we'll make that black. And then on the other side, we can connect this one to ground as well. And I know I'm sort of skimming over how these connections are actually related, but it's all described in this pinout diagram. I can go over that in more depth if we would like later. All right. Yeah, it doesn't look great, but I think the circuit's about set up, so we can start writing the code. Cool. I'm just going to drag this up a little bit. Right. So the first thing I like to do is define which pins I'm using. We have, what's this called? Input 4. And that's on pin 12. 3 on pin 13. Yep. And then we have this enable pin on pin 11, which is a PWM pin. Cool. And we can go ahead and set up the pin modes for these. So we have input 4. I deleted that because that's where it's supposed to be. 3. It's also an output. All right. Cool. Now for the loop. Yeah, so for this part, I'm just going to make the motor accelerate from 0 RPM up to its max RPM, change the direction, and then do the exact same thing in reverse. So go from 0 to max RPM. You can define whatever you would like for your speed control, but that's just what I'm going to do so you can get a sense of how this works. Yeah, cool. So what we would need to do to make it, we have a bit of time here so I can go through this. So like I mentioned, the analog write is a 8-bit output. So we have 255 states that we can control the speed of. So if we just loop through all the possible states, you can get a sense of how the motor works. No, whoops, my bad, I'm used to pressing Control S. All right, so let's just see. Okay, well, it's not spinning, that's not good. Hold on. Did I forget to digital write? I did. Okay, so we have to also define that we want there to be a specific direction for the motor to be spinning at the start. So you're going to have to write one of the input pins is high and one of the pins is low, and that'll define one direction, and then the other direction would be to switch these, have input 4 be high and input 3 be low. That's what I forgot. Also set the enable pin to low just for the start. Cool. All right, so now we can kind of see it's going crazy, hovering around 8,000 RPM. This is because we have no delay, and it's just constantly looping through it. So let's set a delay of 100 milliseconds. Cool. Yeah, so now we can see that the motor is going slowly from 0 up to whatever its max RPM is. We'll just let that finish. I think it should be like 12,000, something like that. Oh, it broke 12K. All right. Well, anyways, I don't know what model motor this is, but oh, 16,000. All right, cool. Yeah, it'll have some sort of high speed, and if you have a circuit like this in real life, you would want to know what the max RPM is before you go up and do this. But just because we're in a simulation, I can do whatever I like. All right, so then just to write out that algorithm I was talking about earlier, where we want it to accelerate from 0 to full speed, stop for a second, and then do the same thing but in reverse. So what we can do is digital write 4 and switch this to high. 3, switch this to low. So you can see that this is the exact opposite of what it was earlier up here. Do we have something in the chat? Sorry, hold on, I don't have the chat window open. Could you explain what an analog is? Sure. Yeah. Essentially, what an analog pin does is it instead of outputting like a 1 or a 0, a digital high or a digital low, it outputs a voltage between usually 0 and 5 volts. It depends on the board, but with this board, I think it's 0 and 5 volts. So in this case, it's an 8-bit output, which means your voltage, if you output let's say if you analog write a 0, that would be 0 volts, and if you analog write a 255, that would be 5 volts. Does that sort of answer your question? Cool. Yeah, and do let me know if there are any more questions. I'd love to answer them. I'm just going to reuse I, because why not? So we can do the same thing here. And to 90,000. And we'll just go ahead and throw these two in to the beginning here so that we can actually see it flip its direction. Cool. Looks good. Why don't we try this? Oh, I forgot a T. My apologies. Oh, I clicked the debugger by accident. Right, so now you can see it's going from 0 to its max RPM. And then on the way back, it should display a negative RPM. That's what this simulation should do. We'll just give it a couple of seconds here, wait for it to run. There we go. And now it's on negative. So you can, well, you can't really tell with this one because there's no easy way to see which direction it's spinning. But you'll just have to take my word that it's going in the other direction. And it says negative RPM. Cool. This is a pretty basic script of how to change the direction and speed of a DC motor. And now we'll get to the challenge part. I think we have some time, 7:45. Okay, we can do this. That's pretty good. Yeah, so like I mentioned earlier, the L293D can drive 2 motors. Why don't we try adding another one to the circuit and see if we can write code for that as well.
So Stephen, how long are you gonna give them?
We can do this for about 10 to 12 minutes, I'd say.
Okay, sounds good.
Sounds good. And oh yeah, there's also this video. Sorry, I have to show you guys this. It's really cool, trust me. Yeah, so this is essentially that same circuit, but in action, there's a resistor because we're using a different motor driver IC that doesn't have internal resistances. And as well, there's a piece of paper you can actually see on the motor here that indicates that it's spinning. Cool. So we'll give you guys a bit of time to work on this. And if someone would like to play music, they're more than welcome to. Although I don't have any music right now. I'm sorry. Yes, the old Zoom box taking up, making a big black box on the screen. I think my screen's being weird.
Steven, what is happening with your computer?
Yeah, that's a really good question. I don't know. Please give me a second.
Oh my.
Okay. Yeah, that was really weird. I'm sorry about that, guys.
All right, ladies and gentlemen, in the interim, I'll be playing a couple of small songs real quick. This is WAP by Cardi B. No, I'm just kidding. I'm not going to play that song. We're going to play you a a jazz standard by Django Reinhardt. I'll See You in My Dreams by Django Reinhardt.
I think Gaurav has me mistaken. I cannot sing. Only if you pick the song for me. Jazz, okay. I will consider it. Yes, everyone do check out the IEEE podcast. We're running one on professional interpersonal development and one on intro to first year. They're both really good. I listen to them occasionally. A lot of new perspectives that I hadn't heard before. So do check them out. Cool. If there are no pressing questions, we might wrap this up in a minute or two so we can get to the final slides. Maybe I'll just go through the challenge now, if there are no questions. All right, seeing none, I'm just going to proceed. Maybe I'll just go to the actual, yeah, let's use this so we can cut down a little bit of time. But I have the challenge circuit built out. So essentially, you just have to make sure that the two inputs, input 1 and 2, and the outputs are both connected just like the top two. Oh, as well as the enable pin, which is now on the left side. You can see it there, enable 1 and 2. So make sure you connect enable 1 and then write about it in the code. Oh, sorry, I should not have moved. So here, I wrote a bunch of functions in this. I'm sorry, that was off the books. I apologize. But yeah, you can see I just set the enable pins up here. So I have 987 for one motor, and then 11, 12, 13. And then you just write the exact same code you did for the first one. And you're golden. Cool. All right, I'm going to pass this off to Selena. Sorry we couldn't have more time to go through this part. Hold on. I will stop sharing.
All right, so now that we've gone through all those demos and those exercises, that you guys have become slightly more familiar with working with those components with Arduino, just like to show some projects that other people have made with the same components that we just went through, and sort of like show you what you can do with that. So first one is an Arduino car. So using the Arduino, we have, instead of what the circuit that Stephen made, we're using a motor driver just to simplify things, ultrasonic sensor and servo motor, and some wheels and some DC motors right here. So we'll just skip to the end to show what it sort of looks like. But this is an object detecting car, so it will avoid any walls, etc. So yeah, that's pretty cool. And we also have, okay, a radar, which is even simpler. It's just using the servo motor and the ultrasonic sensor. And the only extra component here is sort of this UI to show you what the ultrasonic sensor is detecting. So you can see here it's noticing like there's a body spray item there and a ruler and another box here on the screen. So that's pretty cool. All right. And finally, we have a piano tiles robot. So this is just 4 servo motors and then some styluses, as well as some photo detectors there. So the photo detectors are just on the end to check whether the screen is white or black, and then that will send a signal to the servo motor to push down the stylus. All right, we are zooming in a little too far here. So you can see it can go faster and sort of fun to play with, a fun little project to work on using what you already know. So, all right, so that's that. Hopefully this has sort of inspired you to sort of explore the Arduino a little bit more. There are a lot of projects that you can do, and maybe like I know this is online, so it's sort of difficult to show like what it would be like in real life, but if you guys are really interested, you can buy your own Arduino and sort of play around with this stuff. All right, so that concludes our workshop. Before we go, I just like to remind you guys that we have another Arduino workshop if your friends missed this one in January before our Make UofT hackathon. And then we also have our next workshop on October 6th, which is an intro to C programming, as well as our 2 podcasts, First Year Decoded and Professional Interpersonal Development, which is hosted by Martin. And yeah, and all these resources that you saw here today with the slides, the tinkerCAD, and all the videos, those will be sent to you. So you'll have access to all of that. But other than that, if you guys have any more questions, we'll stick around maybe a couple more minutes to answer those. But other than that, thank you for coming, and I hope you guys enjoyed this workshop.